In this segment, we're going to go over the Lighthouse model of a pulsar. The Lighthouse model is the explanation of a pulsar as a spinning neutron star sweeping beams of electromagnetic radiation around the sky. Let's first look at a lighthouse. A lighthouse emits beams of light on either side from very big light sources, and the lighthouse rotates around on its axis. So the beams of light will swing around, and from your vantage points of the way you're looking, you'll see the light blink on, off, on, off, on, off. Because as this light beam swung into view, you would see a big light source, and then as the beam swung away, the light source would disappear, and you wouldn't see anything. And then a few minutes, or maybe 30 seconds later, the lighthouse would once again swing into view, or the light from the lighthouse would swing into view. You would next see another beam of light coming at you, and then when the lighthouse rotated again, the light would disappear. But let's say you're in an airplane above the lighthouse. So you're above the lighthouse, and the lighthouse is swinging around, and it's sending its light source out in this direction. But where you are located, from up there in your cockpit, you can't see the light source because no light is swinging by your cockpit. So the lighthouse isn't going to tip over and send the light up to your cockpit. The only way for you to see the light is if your airplane flew down so it was at the level of the lighthouse, and you would see the light swing by your cockpit. So the lighthouse works great if you're a ship out in sea. But if you are an airplane and you're above the lighthouse, you won't see the light source. So the lighthouse only works in a particular orientation. Let's say there's a very, very hot star located here in the center, and it's blue, as you can see. And what we see is this star's magnetic field lines. They're coming out one pole and going into another pole. So you see lots of magnetic field lines here. Now gas from the star is trapped in this magnetic field, and it gets heated, and it gets excited to emit light, outlining the otherwise very invisible magnetic fields. Beams of light are emitted from this star at the poles. They're coming out at the poles. And unless Earth was located right in the direction of one of those poles, it's not going to see the light at all. Let's say Earth is located over here in the upper left. Well, the beams of light are coming out at the poles, and it's not hitting the Earth at all. Therefore, the Earth would not see this light coming out from the poles. Now, let's say we observed this particular star, and we happen to see this glowing gas. And let's say we determine that the mass of this star on the inside is greater than 3 solar masses. Let's say the mass of the star is less than 3 solar masses. Then this star would be called a neutron star. And I abbreviated the neutron star NS, neutron star. Now let's say the Earth is located so it sees some of the light coming out from the beam. And since the star is rapidly rotating, this beam of light is going to swing away from the Earth and then come back around and swing into the Earth, and then swing away from the Earth and swing in, and swing away and swing in. So from Earth we would see light on, light off, light on, light off, light on, light off, where the vertical axis is the luminosity and the horizontal axis is the time. So what we would see is this pulsating light. It would be light on, light off, light on, light off. If this was the case, then we would not call this system a neutron star. Instead, we would call this system a pulsar. Even though the star is not pulsating, the light seems to be coming from the star in pulses. So we call this a pulsar. Now notice how this pulsating light appears to be like that of a lighthouse. And that's because the light beam is coming towards the Earth, and then it swings around and swings away from the Earth and then comes back around, and we see it again. So it's acting the same way as the lighthouse would. We would see the light on, off, on, off, on, off. Same thing as this system. We would see the light going on, off, on, off, on, off. So we would say this object is a pulsar. The crab pulsar is one of your more famous examples. This is a visual plus an infrared plus an X-ray image of the Crab Nebula. The X-rays reveal an accretion disk and jets coming out. Part of the jets swing by the Earth, and therefore we see the light blinking on, off, on, off, on, off, and hence we identify this object from Earth as a pulsar, even though the central compact object, which I've drawn in black, is a neutron star. Here is an example of an isolated neutron star. Can you see it in the image? It's right there inside the yellow circle. It's called RxJ185635-3754. Now this neutron star may have jets, but the jets may be in the plane of the paper. Let's say the jet is coming out to the right and to the left. Well, then it's going to rotate, and it'll change colors in this direction to green, and then it'll rotate some more in the plane of the page to blue, and then it'll go back to yellow. So it's going to be pointing to other areas, other star systems, but not to Earth. We won't see the light beams pass by Earth. And since we don't see the light beams, we would not call this a pulsar. Because to us, if we looked at the light curve, we looked at how much light is being emitted over time, we might see something fairly constant. And so, since it's not blinking on, off, on, off, on, off, we wouldn't call it a pulsar. We would call this object a neutron star.